Okay, welcome everybody. Well done to making it to the Friday afternoon sessions. Good to see you all here. Our first talk is going to be on quantum signal processing and nonlinear Fourier analysis by Professor Lin.
Thank you, James, and thank you all for staying to the very end of the conference. And I'm going to talk about QSP, which many of you may have heard of, but also nonlinear Fourier analysis. Maybe this is new to most of you. So this is a joint work with three analysts, Michel, Gevorg, Christoph, and also former student Jiasu Wang from math department at Berkeley. And this is the archive number. So I'm going to introduce you the problem, talk about the main results, and talk about some of the main ingredients of the proof ideas. As we know, quantum computing is fundamentally about manipulating unitary matrices, but a lot of things are non-unitary. For example, if we have a Hermitian matrix A, the tasks such as a to the k, A inverse, exponential, those are non-unitary tasks. One of the most efficient ways for handling such kind of problems is called a quantum singular value transformation. Here, because we just write f of A because assume A is Hermitian, but for non-Hermitian matrices, this will be replaced by singular value transformations. The mathematical core of QSVT is a technique called quantum signal processing, presented by Wang here in QIP 2017. And it is really about a theory for SU2 matrices. The idea is if you understand the structure of the SU2 matrices, then you can use a so-called lifting idea called the cubitization to work on arbitrarily large matrices. And this talk is only about SU2 matrices. Specifically, the task of quantum signal processing is you take a scalar x that's real on -1 to 1. I can write it as a cosine theta. There is x rotation matrix denoted by W, parameterized by lowercase x. We choose this is so-called symmetric phase factors. It's a little bit of restriction, but makes the discussion concrete. Symmetric phase factors denoted by psi, such that I start from some sort of z rotation in the middle every time I multiply 2wx on the side and multiply the symmetric phase factors and let it grow. The task of quantum signal processing is that I will end up with a matrix that is of size 2 by 2. I take the 1, 1 entry, the top left entry of it, and adjust the phase factors to fit some real polynomial fx. Specifically, I take the imaginary part of this 1, 1 entry, and I want it to be equal, not approximate, equal to fx for some polynomial for all x that's on -1 to 1. And this is called quantum signal processing. Once upon a time, phase factors used to be hard to compute, and that's actually not that many years ago. And in this influential paper by Andrew Charles and collaborators, they compared a number of techniques, including the newly developed quantum signal processing back then in 2018. And in this appendix, they also tried the optimization of the phase factors. At that time, concluded calculation of the angles, even for degree 32, seems to be prohibitively large. And that's if you directly solve the inverse problem by brute force. There has been tremendous progress on this, actually shortly after the PNAS paper, the QSVT paper, and also in the work by Zhou Ha. They have proposed rigorous methods to find the phase factors. The idea is to compute the roots of a high-degree polynomial to high precision, and this is not numerically stable. By not numerically stable means that if the polynomial degree is d, numerically stable algorithm should use polylogarithmic number of bits in d to find the phase factors, but the algorithm here uses a linear in d bits. There have been many works successfully avoid the root finding problems, but all these works, the techniques are quite difficult to find a rigorous proof. In the past few years, we followed a very different route called iterative methods. We have some partial proofs. Some of them, some of the best methods numerically called Newton's method, and but we couldn't have a full proof. In practice, this problem is pretty much practically solved because we can now calculate polynomials of degree that is way larger than 10,000 we don't think this is gonna, the real application of this will go beyond this within the foreseeable future. But there is still an open mathematical question, which is how to understand the structure and find a provably stable algorithm to find phase factors for all polynomials that admits a QSP representation. So in this work by my collaborators in October 2023, they wrote this quite shocking paper. I give a talk in an occasion in the summer of 2023. 3 months later, they posted this online. Realized my collaborator, Christoph Thiele, had a head start because he wrote a textbook with Terence Tao on nonlinear Fourier analysis. So the book is just about SU11, but the story of the QSP here is about SU2. This slide may look a little bit scary, mostly for you to take a picture. So, there's a natural class of functions is integrable things called a Zego function. And specifically, if you consider any function f, that infinity norm is bounded by anything less than 1, this satisfies the integrability condition. And we want to find the suitable set of phase vectors called P, which is pretty natural. Note that here, the set of P can be infinitely long, which means that the function we're talking about may or may not be a polynomial. Quick review of linear Fourier analysis. So the unit disk is called D. The unit circle is called T. And the Fourier analysis, linear Fourier analysis says, I start from 0, just a scalar, g minus infinity. And I just sum up every time fk times z to the k. And I add this up to infinity. And this so-called g infinity is just the Fourier series. There is a famous Parseval-Plancherel identity, says that on the unit circle, the L2 value in the real space is equal to the L2, small L2 sum in the Fourier space. Right? This is the undergraduate linear Fourier series. Nonlinear Fourier analysis for SU2 is a generalization of this. For simplicity, talk about compactly supported sequence, means the sequence of finite length, beyond that is 0. We start from identity. We, instead of sum, we multiply. Every time you multiply a matrix in SU2, if this is the first time you see it, it doesn't look like SU2, you can just check that. It's a unitary and has a unit determinant. So you multiply infinite of those things, it's still in SU2, and you look at the k equal to plus infinity limit, and this is called a nonlinear Fourier series. This encodes a parameterized matrix in SU2, have the following form, AZ/BZ, that's the top row. The bottom row is related to the top row by a star operation. On the unit circle is just complex conjugation, and within the unit circle, things are a little bit complicated, but basically it's related to complex conjugation. There is a natural determinant condition that the first row or any row must sum up to 1. And there is a direct connection between QSP and nonlinear Fourier analysis. The theorem is is a bit chunky, so I'm not showing it here. But believe me that solving this problem is equivalent to solving QSP. The result they proved in the first work was that for every function f in S eta, remember S eta is pretty much the distance between the infinity norm and 1. If this eta, the distance is bigger than certain constant, here it is 1 minus 1 over square root of 2, then they can prove that there exists a unique QSP phase vector sequence with L2 convergence to F. So this is not just a polynomial representation anymore, it's a function representation. And also satisfies a nonlinear version of the Plancherel equality, and where the left-hand side should be interpreted as the L2, nonlinear L2 in the Fourier space, and the right-hand side should be interpreted as the nonlinear version of the L2 in the real space. So there are two drawbacks. One is that this bound eta is highly technical, is based on a certain fixed point theorem, and just beyond this, things don't converge. And a quantum algorithm, there's a slight disadvantage when eta is large, means there's some reduced success probability. You can put another layer of amplitude amplification on top of that, but still it would be nice to ask whether you can avoid that. This is where our paper is about, and which extends this to arbitrary Zagel function. What it means is that you can generalize of the previous result to any eta that is bigger than 0. When eta that is going to 0, this is what Eichstrom's group talk about, the fully coherent limit. And but there's a important technical development, which is previously there was a fixed point theorem. We throw that away and replaced by a technique called the Riemann-Hilbert factorization, which I'm going to talk about. The results is for every function f in the Zagel class, there exists unique phase factor L2 converges to f and satisfies nonlinear Planck-Rail inequality. This theorem has a direct algorithmic implication. That is, for every even is a technical thing, even input polynomial f with degree 2d, there exists a deterministic algorithm to find all the phase factors that scales polynomially in D and also is numerically stable using log D over epsilon eta bits of precision. But it does this, achieves this task, achieves this goal in a rather unusual way. So for those of you who have seen QSP before, seems like everything is just totally entangled. I mean, really, you tune some of the phase factors, it affects everything. But my claim is there is the deterministic algorithm to compute phase factor one by one. Just compute one and completely throw away the rest of them, and it still works. And you just do this one by one, and there's no accumulation of error. This is the first provably numerically stable algorithm for OF. There's some straightforward generalization to all the polynomials, and the key technique is called the Riemann-Hilbert. Let me use the remaining few minutes to talk about the proof ideas. And the first is that the Riemann-Hilbert factorization tries to solve the following problem. So if you have a sequence that's compactly supported, there is a well-known technique that allows you to start from the boundary of the phase and just figure out one and eliminate that and figure out the next. And this is called the layer stripping algorithm that actually dates back to Isaac Schur in 1917, but in a different context. But what if this sequence is in L2, which means that it's not compactly supported? I mean, you cannot start from some edge. This is the Riemann-Hilbert factorization is trying to do. It says for every function, every representable polynomial, matrix polynomial G of Z, it's actually Laurent polynomial G of Z, and you can always factorize it into G less than n times G bigger than or equal to n. And each is representable by a nonlinear Fourier sequence, but the first G less than n is supported on minus infinity to the n. The other one is supported on n to infinity. If this can be done, you can apply the layer stripping and, for example, to G bigger than or equal to n and find the phase sequence at n. That's the idea. So layer stripping, or some people in the community call the peeling algorithm, is a special case of a Riemann-Hilbert factorization. What it does is to solve a linear system of equations. There's nothing mysterious about that. The big question here is this linear system stable? That means from a numerical analysis perspective, whether you can bound the condition number. Open question, because based on earlier results by Zhou Wang Ha, he proved that you can use d bits to compute the phase factors. And indeed, there are counterexamples that if you use less than d bits, the method is not only theoretically, you cannot prove the results. Numerically, it's just non-stable. It's garbage. So it seems like really there's no way out. Actually, no, because QSP offers a special structure. It's essentially a matrix completion problem. It says that what we want is a part of the 2x2 unitary matrix. In the language of nonlinear Fourier transform, what we want is the information f, the polynomial, is in this BZ. And this A, you can choose whatever you want. Then it has been known that for every given B polynomial, there exists a combinatorially many AZ through some root finding procedure, but it is unclear which one is better. That's the thing, unclear from the previous literature. The key insight of this paper is that if you choose this A star Z to be a so-called outer function, there is a specific definition of outer function in the field of Hardy function analysis, which is a subfield of a complex analysis. Roughly speaking, a function is outer if it can be written as exponential of an analytic function that is bounded in the unit disk. That's about it. And if you choose this A star to be outer, then something very, very good is happening. In fact, this corresponds to one of the combinatorially many AZ. Just for the experts, that corresponds to the case where you choose all the roots to be within the unit circle. The proposition technical result is that given some suitable AB, if A star is outer, then Riemann-Hilbert factorization is numerically stable. What you prove is that when A star is outer, that linear system can be written as identity plus M. M is an anti-symmetric matrix with a purely imaginary spectrum, and therefore condition number is less than infinity, period. So I didn't tell you how to get this outer function. There is an algorithm called the Weiss algorithm. It involved some sort of like a Hilbert transform, which is implemented with the Fourier transform. For that, you can check the paper. So the algorithm flowchart is that you start from an F, you run an algorithm called the Weiss, dates back to Gilder and Mary Weiss in 1962. So you run a Weiss algorithm to find an A star that is outer, which is numerically stable, and the cost is this plus part. You only do that once. Then, for every phase factor you're interested in, you run Riemann-Hilbert, that the worst case algorithm is just a Gauss elimination, that's d cubed. You find the one phase factor. And then you, for all of them, you multiply another d, that's d to the 4 plus blah, blah, blah. You've seen before. And every step is numerically stable, and therefore you use log d number of bits. There have been some further developments since then. It is worth mentioning that Hongkang Li and who's here, and Alexis Ying, last October, they enhanced the efficiency of the algorithm by developing a so-called half-Cholesky algorithm, reduces d to the 4 to d squared. The reason is that in the D linear systems, there are just tons of redundant computations, and they have found a very good way to reduce the computation. But the idea is still the Weiss plus this Riemann-Hilbert-like ideas, although it's significantly modified. A lot of the people in the community knows that Nathan Weeb and collaborators developed this generalized quantum signal processing, which removes the parity constraint, but adds an analyticity constraint. And so I learned during the conference that some people, maybe here in the audience, are working on the equivalence between the GQSP and the nonlinear Fourier analysis. Well, there is a work in preparation with Hongkang Ni, Rahul Sakar, and Alexis Ying, showing a few new results. The first one is quite surprising. Layer stripping can be numerically stable when A star is outer. Although I said Riemann-Hilbert is great, but turns out there's deeper reason that lies underneath this this condition, this A star outer condition. And furthermore, we can develop an even faster algorithm, which is a generic fast inverse NOFT on SU2 with cost that's linear in D. That should be a lower bound, because at least you have to look at every entry once. Well, it's another thing, we also provide a unifying perspective of QSP and GQSP. We have seen in the poster sessions, I think, there are a number of generalizations to of QSP. There are multivariables and nonlinear Fourier analysis in higher dimensions. I think those are quite interesting. With this, I'd like to thank you very much for your attention.
Do we have any questions?
Thanks for the nice talk. So I was wondering, do you have even just a high-level intuition on why an a non-outer A could provide numeric instability?
Yeah. So the high level, I think there are a number of ways to understand this. I think I'm not sure you take this as a high level because it is pretty technical. That only when A star is outer, you compute some Chebyshev coefficients of B over A star, and you find that it's purely imaginary. That's the basis why the spectrum is the eigenvalues are purely imaginary. And when the condition is not satisfied, you cannot prove such a result. But it doesn't mean if and only if. We don't have a very sharp characterization beyond the outerness, when this would be stable. There are some other ways to understand this from displacement structure, which is our work in
progress. Thanks for the talk. So you mentioned some potential generalizations to higher dimensions. Do you have any potential applications of that, or?
Nope. Short answer. But I think you here may have some better idea than we have. We don't have a good
So I guess a lot of the work on phase factor computation considers doing it for general functions and gives bounds for that case. But I guess there's particular functions that we're interested in for applications, like the Jacobi-Anger expansion for quantum simulation. Do you see any scope for giving faster algorithms, like for particular cases of interest?
I don't see how, though. I mean, for the this result is for any f that's already been turned into a polynomial or even not a polynomial. And as long as the infinite norm is bounded by 1, and everything is just is unique. There's no degrees of freedom to it. So, yeah, so I don't have a good idea how to explore. Oh, there's a, good.
On the phase factor calculation, maybe for high-dimensional systems, we have descaling. Do you have a sense like how the scaling should scale for like local dimensions?
Fantastic question. I have no idea how that works because, yeah, a lot of things breaks when go to your SUD case.
Thank you.
Good question. In fact, going from SU11 to SU2 involves some non-trivial analytical things. So going to, even I don't see how to go to immediately to any SUD.
I know that some methods in nonlinear Fourier analysis have historically been used to solve certain types of nonlinear differential equations. I'm wondering if there's any means by which this type of analysis helps you not only find phase factors, but maybe also apply to the methods that SU11 variants of NLFA were originally used for. Are there any applications in that direction?
Right. So they have been used in some to solve some integrable systems. Maybe one can think of interesting analytical systems that can be solved with this SU2 variant. But also looking at the historical literature, nonlinear Fourier analysis is not the only way to solve those integrable systems, right? And so I don't know whether this will allow you to find new integrable systems to solve at this point.
I think we've got time for one more.
I'm wondering if you could comment on the, let's say, stability of this QSP circuit to errors in the angles.
Mm-hmm.
To be more concrete, let's say you use QSP to simulate time evolution, and for whatever reason it happened so that the depth of your QSP circuit is exactly the same as depth of the Trotter circuit. You can always like artificially choose time duration and epsilon so that they would be the same. And now you allow a tiny error in your gates. Which one you think would be more sensitive?
I think there immediately come to my mind, there are two bounds. And one is if you know everything, like the block encoding matrix UA, and then you can just apply the linear growth argument, right? I mean, each one make an epsilon error, you grow it linearly. There's a little bit better bound, and that's in the archive version of the original QSVT bound called the robust QSVT. We have authors sitting here. They will be able to point to you which section to look at.
Thank you.
Thank you for the nice questions. Let's thank the speaker again.